Now biphenyl. How would we get biphenyl? There's no reaction we have seen in any electrophilic substitution that phenyl will substitute a hydrogen, that you will get a biphenyl from benzene ring. I'll be using one of the reaction here that you must have studied in hydrocarbon, and which is a common reaction, and that's the reason I'm using it here. That is Wurtz reaction. Now Wurtz reaction result in formation of RR or PH. It result in formation of a symmetric hydrocarbon. That means if you have RX, you add sodium to it, that result in formation of RR, right? So you understand it from here. Now if you have PHX, if you will be adding sodium to it, that will result in PH. So all you need to get is PHX, and PHX can be developed in a single step by halogenation. You carry out chlorination or bromination or iodination. Iodination is slow because of sluggish nature of iodine, but chlorination and bromination are good enough. If you have benzene and if I add chlorine, AlCl3, I'll get chlorobenzene. And if I add sodium to this will give me directly in one step biphenyl. PHCl will result in PHPH. The mechanism of this I am not telling you. For your own benefit, we will see this at the right place when I'll teach you reactions of hydrocarbon. But this you must know at least by name. There's a reaction called Wurtz reaction which produces RR when you add sodium to RCl. Now one thing out of league I can ask you, what will be the solution, what will be the solvent in this reaction? Can we take water as a solvent in Wurtz reaction? They ask you in CBSE boards exams, can we take water as a solvent in Wurtz reaction? And you'll answer, no, we can't take. Why? Because the reagent in Wurtz reaction is sodium, or sodium catches fire in water. For that simple reason, we can't take water as a solvent in a reaction where sodium is a reagent, or any other active metal for that matter. You can't take water as a solvent even if you have magnesium or zinc or potassium. Now let's go ahead. Now you have to create nitrosobenzene from benzene. Now this will be a slight extension of the reactions that we have studied, and this may be asked in any other competitive exam. You have been taught how to get nitrobenzene, you haven't been taught how to get nitrosobenzene. Now the mechanism, if I recapitulate you how you got nitrobenzene from benzene, from benzene you add nitrating mixture to this, and somehow you created NO2 plus. When you create NO2 plus, then this NO2 plus gets added on benzene and you get nitrobenzene, right? This will be the motivation for us to think for a mechanism to get nitrosobenzene. To get nitrosobenzene, if we manage to get nitrosonium ion, NO plus, then this NO plus will get added to benzene and give us NO on benzene. That means nitroso on benzene. So we can get nitrosobenzene if we get nitrosonium ion, like we got nitrobenzene as we got nitronium ion, right? Nitronium ion, if you remember, we got from nitric acid, where we had nitric acid like this. Apart from nitric acid, we took a stronger acid, that is sulfuric acid. That sulfuric acid protonated this nitric acid, make this as H2O plus. This got removed, and taking away the electron of this bond, resulting in formation of NO2 plus. Instead, if we take nitrous acid, this was HNO3, this is nitric acid. If we take HNO2, nitrous acid, one oxygen less, and again take a strong acid like sulfuric acid, that will protonate this nitrous acid, then again H2O plus will be formed. Again it will be removed off as water, taking away the electron of this bond, forming plus charge on this nitrogen. So as we got NO2 plus here, we will get NO plus here. So this resulted in formation of nitrobenzene. This will result in formation of nitrosobenzene. Easy enough. So they may go one step ahead, whatever is written on in your book, and ask you to form or produce this kind of compound. So basic structure you know, the theory you know. Now you have to use your mind to create a slight extension or to cope up with a slight extension of those theories, and that is the most that is expected out of you. So in order to create nitrosobenzene, what you will do is you will take nitrous acid HNO2 plus a strong acid like H2SO4 on benzene. This will give you nitrosobenzene via this mechanism, right? Now let's go for di-substituted products. If I want to create this, you have a benzene and you have alkyl group at meta position of aldehyde group. That means you have a meta alkyl substituted benzaldehyde. Now when you have, as we have solved certain problems in the previous lectures, as you have two substituted group on benzene, then you have to think about the directing effect of each of the group. Suppose if I take R, then you have to think about the directing effect of R. Now this we have very well discussed the directing effect in the last lecture. In case you have a problem, then please go back to the previous lecture and listen them again. The directing effect of R is ortho para. R directs to the ortho or para position to the incoming electrophile. Now if you take R, if we add R group first, or if we carry out alkylation first, then this alkyl group will direct the new incoming electrophile to ortho or para position, but this aldehyde group is at meta position with respect to this R. So if you carry out alkylation first, then by no way you can get this aldehyde group at meta position, because this alkyl group will direct it to ortho or para position. So the other way round, if you carry out if you bring aldehyde group first on benzene, then this aldehyde is meta directing. How would you know? You would know by looking at the atom which is directly attached to benzene ring, since this is electron deficient. So this is, the whole group is meta directing. Why it is electron deficient? Because it is attached to a very electronegative atom, that is oxygen, which is pulling electron from two bond, the double bond between carbon and oxygen. So this carbon is electron deficient, so electron out of benzene ring will diffuse into the orbital of that carbon. So electrons will diffuse out from ortho and para position, making them electron deficient. So relatively meta will be more electron rich, so incoming electrophile will go to meta position. That makes this aldehyde group meta directing. Alright, this part we have discussed in great detail. We don't need to talk about it now. We know and we understand this before. At least I expect you that you understand the directing effect very well. Now assuming that you understand, this aldehyde group is meta directing. If you bring aldehyde group first, then there's no problem. Then if you carry out alkylation, then the incoming alkyl will go to meta position straight. So the step to produce this compound from benzene would be, you start from benzene, bring this aldehyde group. Now you have learned how to bring aldehyde group. I have taught you in the previous lecture. To bring aldehyde group, you have to take carbon monoxide HCl in presence of AlCl3. This carbon monoxide and HCl effectively is this acyl group, and if you add AlCl3 to this chlorine is removed off as Cl minus, forming this acylinium ion, and this acylinium ion is nothing but aldehyde group. So this goes and get attached to this via formation of sigma complex and all the steps we have seen before. So this will directly give a aldehyde group on benzene ring. So that will result in formation of benzaldehyde. Benzaldehyde is now a meta directing group. So if we carry out alkylation on this benzaldehyde, alkylation can be carried out by RCl and AlCl3. If we carry out alkylation in this group, then the alkyl group will go to meta position and you will get the required product. So this is how basically you have to think of. If we want to get ortho chloro nitrobenzene, now this is nitrobenzene. Chlorine is at ortho position with respect to nitro, right? So we can call this as orthochloro nitrobenzene, or this can equivalently be also called as ortho nitro chlorobenzene, because nitro is at ortho position with respect to chlorine, whatever. We have to produce this from benzene. Now looking at the groups, one is chloro. Now you have to look for the directing effect of chloro. Chloro, as we have seen in the previous lecture, or any other halogen for that matter, is ortho para directing, although they are deactivating, but still they are ortho para directing. This is a very important fact that you have to remember in organic. This will be used many a times ahead. If you look at nitrobenzene, nitro is deactivating, very powerfully deactivating, and hence this is meta directing. So if you carry out nitration first, or carrying out nitration will create a problem that it will deactivate benzene ring to such an extent that further substitution, electrophilic substitution reaction will be very, very sluggish. So we avoid nitration first in the first step itself. Plus, even if you carry out nitration and even if the reaction occurs with the very sluggish rate, still we won't get chlorine group at the nitro ortho position with respect to nitro, because nitro group is meta directing. The chloro group will go to meta with respect to nitro. So the smart way to produce this would be, rather the only way to produce this would be, carry out chlorination first and then carry out nitration. So if we carry out chlorination first, chlorination can be carried out directly by chlorination reaction, one of the reaction that we have seen in those 5 reactions of electrophilic substitution. This will bring about chlorine on the benzene ring directly. And now if we carry out nitration, then what is the directing effect of this chlorine? Ortho para. What do you mean by that? Chlorine has ortho para directing effect. That means chlorine directs the next incoming electrophile either to ortho or to para. Now we haven't had much of the discussion on the major product. Which one will be major, ortho or para? The time has come to have a discussion now. Now since chlorine is ortho para directing, that means chlorine will be directing the new incoming electrophile to 3 positions, as they are 2 ortho and 1 para. These are ortho para positions. Now incoming electrophile will be getting directed to these 3 positions. Now these 2 will be similar. The IUPAC name will be same. If you flip them, then they are interconvertible. They are the same exactly. It doesn't matter if the group is attached on this ortho or this ortho. If you flip it over, one will be converted to another. So basically they are same, they are identical, so there is no difference. So one class of product will be ortho substituted, whichever ortho it is, doesn't matter. The other class of product will be para substituted. Now which one should be major, ortho or para? In organic, when you are asked to write the product, basically it is understood that we have been expected major product out of us. You don't have to write all the product. So generally we show only one product, either ortho or para, whichever is the major. Now how would we decide whichever is the major? The rule of the thumb is para product is always major product unless there is hydrogen bonding at ortho position because of steric hindrance. Now this chlorine is a atom of 3rd period. This is sufficiently big atom, bigger than all these carbons. The size of one chlorine will be bigger, more than 2 carbon atoms put together. Chlorine is a big atom. If you bring a big group, this nitro group, nitro has 3 atoms, 2 oxygen, 1 nitrogen. Nitro is a bigger group. If you bring a nitro group here, then because of this chlorine and this nitro group, there will be steric hindrance, and that steric hindrance will create problem, right? So ortho position, generally you have enough steric hindrance to make this ortho substituted product as a minor product. So the rule of the thumb is The para product is the major product because of steric hindrance at ortho position. But if you have hydrogen bonding at ortho position, then ortho becomes the major product. We will see this in the next problem, why with hydrogen bonding you have a major product becomes the ortho substituted product. But for the timing, if you don't have hydrogen bonding, then always and always para substituted product will be the major product. Now hydrogen bonding, we'll talk about hydrogen bonding in the next problem. For the time being in this problem, if you carry out nitration now in the chloro substituted benzene, that means on the chlorobenzene, then the nitro group is not going to go on ortho position as it is desired in the problem. Rather it will go to para. Why? Because there is no hydrogen bonding at ortho. Instead there is steric hindrance. So to minimize the steric hindrance, to get rid of that steric hindrance, the nitro group will go to para position. But we want it at ortho. So how to get it? So here we come at a very important stage of this topic that will have the sense of completeness of this topic, and this will be a very important concept again that you have to clinch with. Remember when we studied sulfonation, I told you that sulfonation is reversible reaction and we can use that reaction to our advantage. Now this is a high time to use that reaction to our advantage. What we will do is we will carry out sulfonation on this. If we carry out sulfonation, what will we use? We use fuming H2SO4. Fuming H2SO4 means sulfur trioxide dissolved in H2SO4. If we use this, then sulfonyl group will get attached on benzene ring. That means we will get benzene sulfonic acid or sulfonic acid substituted product. Where this sulfonic acid group will go, at ortho or para? This is a new incoming electrophile. Now the directing effect of chlorine is ortho and para. Because of steric hindrance, again this sulfonic acid group will be a much bigger group than nitro group because it has 4 atoms. Bigger atoms. Apart from this, we will have a hydrogen as well, and sulfur, that too from 3rd period. So it's a big group. By no way it can go to ortho because there will be huge amount of steric hindrance, so it will go to para. So we will get is para chloro benzene sulfonic acid. Okay, now if we carry out nitration, para is blocked, para position is already occupied. Now if we carry out nitration, then nitro group has no option other than these two ortho, because para is blocked, it can't go to para. Para already is making a bond, so it will be forced to go to ortho position. If we carry out nitration on this by adding nitrating mixture, nitro group will get added to ortho position as we wanted, right? But we didn't want the sulfonic acid group at para position. So what we do is we carry out a reversible reaction. That means if we heat this in presence of slight acidic medium, if we heat this, then because of heating, the sulfonic acid group will be thrown out because it will go to water forming sulfuric acid, releasing sufficient amount of heat. So the reaction will be proceeded in backward direction, and this sulfonic acid group will be dissolved in water forming sulfuric acid, right? So this will be a reversible reaction, and we can use this reversible reaction to our advantage to block para position. So because the major product is the para, and if we want the ortho substituted product as major, so we use most of the time, very often we use this reaction to block para, because if once para is blocked, the new incoming electrophile will go to ortho, and hence we can get ortho as the major product. If you don't do this, then the nitro would have gone to para because of steric hindrance at ortho, and we would have got para substituted nitro. We would have got nitro group at the para position of chlorobenzene rather than at ortho position as is desired. that would have been a wrong answer. That would have been a minor product actually if you get a if you carry out nitration directly on chlorobenzene. So that would have been a wrong mechanism, right? So whenever this kind of product is given, we have to make sure that this product is the major product, not one of the many products. So this way it is made sure that this is the major product after blocking para, and again removing off this sulfonic acid group by reversibility, using reversibility, right? This is another important concept from this topic.